This problem is a good review of the mean value theorem. The mean value theorem, you're expected to know it, so it is on your formula sheet for game day. They were nice enough this particular year to actually tell you what the mean value theorem is. There's no guarantee of that, so make sure and look over it before paper 3. But here they told us the mean value theorem states that if f is a continuous function on a closed interval, a to b, and differentiable on an open interval from a to b, then f prime of c equals f of b minus f of a over the quantity b minus a for some c, an element of the open interval. Okay, so when you look at this, remember that they're saying if your function is continuous on the closed interval and differentiable on the open interval, then there is a spot somewhere in the interval where the slope of the tangent line is equal to the slope of the secant line. So if you remember, we looked at that, and here we just have a nice function that's continuous on the closed interval, it's differentiable on the open interval. Notice this interval is from A to B. Okay? And so if we draw a secant line, okay, so that's just a secant line from the starting at A, f of A, to B, f of B, and the slope of this line is just the rise, f of B minus f of A, over the run, b minus a. They're saying that it's guaranteed that somewhere in the interval the slope of the secant line is equal to the slope of the tangent line. Okay, and so you can just kind of look. Do you think there's any spot along here where the slope of the tangent line would be equal to the slope of this blue line here? So we're just going to slide it. And there it's marked one spot for us. And here it's marked another spot. So there can be more than one spot, but they are guaranteeing that there exists at least one point in the interval between A and B such that the slope of the tangent line is equal to the slope of the secant line. Okay, so we're just going to close that out. Okay, and so that's what it's looking for there. So it says find the two possible values for C for the function defined by this cubic function on the interval from -3 to 1. So this is my A and B. And the polynomial is very well behaved. We're not expecting any asymptotes, any spots of discontinuity. And so it's reasonable to say that it's going to be a continuous function. But we'll just go ahead and mention that to them. Okay, so we'll just make them aware that f of x, just grab a different color here, f of x is continuous on the closed interval and differentiable on the open interval. So we are stating that it meets the conditions of the theorem, and so that means there's a spot where the derivative equals the slope of the secant line. Okay. Now, I need to take the derivative of this. So the derivative of this is easy, power rule 3x squared plus 6x. I am evaluating at C. Now, they're not going to get you if you don't put in C, but we'll go ahead and do that. So this will be all in one, the derivative and evaluated at C, so that would just be 3c squared plus 6c. Okay, so the slope of the tangent line, which is the same as the derivative, will be equal to the slope of the secant line between these 2 points. So, again, this is A, and this is B. So this would be f of 1 minus f of -3 over 1 minus a -3. Okay. Now you're substituting these into the original function. Okay, the 1 all the way through, the -3 all the way through. When you do that, you'll have 2 minus a -2 over 4, which just comes out to be 1. So you have 3c squared plus 6c equals 1. And then that's just a quadratic, so you can certainly solve it with the quadratic formula. You can solve it with the quadratic formula, then you can solve it using polytools, which is what I would recommend. And so with polytools, you would get 2 values. Okay, and I'll leave that to you to verify. Now, The next thing it says is illustrate this result graphically. So they want to know, same thing when calculus in motion is demonstrating, do you know what this looks like? And so what I'm going to do is just go ahead and graph the function on my calculator. So this would be x cubed plus 3x squared. Oops. Need to go down from the next one. Plus 3x squared minus 2. Okay, and I really only need to look at this from -3 to 1. So for me, I prefer to change my window settings, make this show me from -3 to 1. So just looking at the area that they want me to. Okay, so what you should do is just go ahead and make a sketch of that. So I'm going to be doing that. You, as you know, would be better off looking probably at the sketch on your screen. Might be a little easier if I had bothered to go by ones, just because this auto sometimes looks like a little bit gross. Make it a little more clear. Sketch it. Okay, so I'm going to be sketching that on my paper here, just showing from -3 to 1. So I'm going to show all of these things. It looks like we've got the point 1. Well, what's that look like? -2, 2, perhaps. Doesn't really matter. Looks like it's crossing at -1, 0. Looks like we got 0, -2. And of course you can look, get a few points off the table if you'd like, just to kind of make life easier. Maybe just a couple of those might help me to have that 1, 2 there. And just verify that I was right here with a couple of those. Okay, so got my looks like we had -3, -2. Okay, -2, 2, -1, 0, 0, -2, and 1, 2. Okay, so I've got those points. I'm just going to try to draw my curve there between those. Okay, and do have a ruler on this. Okay, so when they say illustrate it graphically, this is the slope of the secant line. I'm going to use different colors. You're not going to have different colors. Okay, but here, this would be the slope of the secant line. And they're saying I'll have that same thing at about -2.15. So I'll just kind of, oh boy, that looks a little rough. Okay. And then also at 0.155, so maybe right about here. These should all look parallel. I didn't do a fantastic job. Here's a little bit prettier version of the same thing that I did earlier. Okay, but here basically what you have, and you're trying to show them that you knew it was at 0.155 and at -2.15. But here, these are the slopes of the tangent lines at those points. Okay, so just try to show them that you understand that. Again, there's a little bit nicer version of that. Okay. Alright, so the next part says the function f is continuous on the closed interval, differentiable on the open interval, and the derivative equals 0 for all the x in the interval. Okay, so this is even, this is more specific than Rolle's theorem. Okay, so remember that Rolle's theorem is just a special case of the mean value theorem. Rolle's theorem says if you have a function and it starts and ends at the same value, so f of a is equal to f of b, then there's a spot in the interval where the derivative equals 0. Well, that's just because the slope of the secant line is 0, so somewhere you're guaranteed the slope of the tangent line is equal to 0. But this isn't talking about Rolle's theorem. This is much, much more specific than even Rolle's theorem. It's saying if the function is continuous on the closed interval and differentiable on the open interval, and you know the slope is equal to 0 the entire time, show that the function has to be a constant. Well, that kind of makes sense. If the slope is 0 the entire time, then the function must be a constant. Okay? So here, the function wasn't a constant, but the slope wasn't 0 the whole time. That was just the slope of the secant line and the slope of the tangent line and add a couple of points. Okay, so this is just a, it's okay, but basically what they're going to have you do is just suppose that you have some x that's in the interval. Okay, somewhere is an element of the interval. Okay, and so then, by the mean value theorem, there exists a c such that, st for such that, the derivative is equal to, and I'm just going to do the slope between x and a now. And we're saying that that has to equal 0 because it's equal to 0 the whole time. And the idea here is if the theorem is true, I'll just write this out for you. On a to b, it's also true on any x1, x2 belonging to the interval. Okay, so if you know that this is equal to 0 everywhere, okay, then you know the numerator has to equal 0. Which means that f of x equals f of a, so the function, in other words, itself is equal to f of a, which is equal to a constant. Okay. Now, we're going to get even a little more detailed. So the last part of this problem says, hence, so using what we just did, prove that for x an element of 0 to 1, 2 arc cosine x plus arc cosine of the quantity 1 minus 2x squared equals pi. So somehow I have to use what I just had. Okay? And what I just had was that if I can show the derivative is equal to 0 the entire time, then the function must be equal to a constant. So what I'm going to do is see if I can start with finding the derivative of this. Okay, now I am applying the mean value theorem here in the last two parts, so I'm just going to go ahead and make a statement that this function that they gave me is continuous on the closed interval and differentiable on the open interval. Now you might want to graph it, take a look at it if you got a chance. Just make sure that that it looks smooth on the interval, no discontinuities, all that type of thing. Okay, but we're going to take the derivative, so that's my function. And arc cosine is not one that we use all the time, so I'm going to go to my formula sheet and get this rule. Okay, so I'm just going to write this rule off to the side. So I've got arc cosine x, the derivative is negative 1 over the square root of 1 minus x squared. Okay, that's not one that we use all the time. I'm just going to write it down. Okay. So now when I take the derivative of this, I would have 2 in front, constant comes down, and then that's just the rule for arc cosine x. So I'm just going to write that. Okay, this is where the problem started. And then here I'm applying this rule to this. So what I'm substituting in instead of the x is 1 minus 2x squared, and then I'm going to have to remember to say times the derivative of the inside function. Okay, so I'm going to have negative 1 over the square root of 1 minus, instead of x, I'll put 1 minus 2x squared. And that quantity is supposed to be squared. So instead of the x right there, I just put what I was taking the arc cosine of, and then times the derivative of this inside function. Okay, so that's just derivative 1 is 0, and then this would be negative 4x. So I'm just going to put that in the numerator. And we're just going to work this out and see what we get. So this looks like negative 2 over the square root of 1 minus x squared. In the numerator here I have positive 4x, and in the denominator I'm going to FOIL this out and see what kind of stuff we come up with. So if I FOIL 1 minus 2x squared, quantity squared, I'd have 1 and then minus 2x squared minus another 2x squared, so minus 4x squared. And then I would have negative 2x squared times itself, so that would be a positive 4x to the fourth. Okay, so let's see about simplifying that. Okay, so the 1 is going to distribute. So I think the easiest thing to do here might just be to change this to positive, go ahead and distribute our negative through. Okay, so this is going to cancel. And I would just have, under the square root still, 4x squared minus 4x to the fourth. Okay, it does look like there's some stuff we can factor out there. So if we do that, there's a 4x squared common to both of those terms. That would leave me 1 minus x squared. Now that's kind of nice because we're getting closer to having a common denominator here. So we have negative 2 over the square root of 1 minus x squared. Here we can take the square root of this. So square root of 4 is 2, square root of x squared is x. Now don't try to take the square root of something that's added and subtracted underneath the square root. You can only do that for multiplication. Okay, but nice, right here, x's will cancel. 4 over 2 is just 2. So if you look, what you have is negative 2 square root of 1 minus x squared plus 2 over the square root of 1 minus x squared, which is 0. So if you look back, they said that if the derivative equals 0 for an entire interval, then the function is just a constant. So that means no matter where you evaluate the function, it's going to be the same thing. Okay, so you can just evaluate it anywhere. Okay, so it's constant, according to what we just did before, on the interval. Okay, because we know that the derivative equals 0 everywhere on the interval from 0 to 1. So we can just find the value at any point. Well, if I have to substitute into this original function, which is 2 arc cosine x plus arc cosine 1 minus 2x squared, anywhere on this interval, I mean, 0 seems like a really nice number to put in. I could probably put in 1, 2, or not 1, 2, but 1 as well. But I think I'm going to go for 0. So I'd have 2 arc cosine of 0 plus the arc cosine of 1 minus 0, so just 1. Okay, so here we have 2 times the angle whose cosine is 0. Now I want to give you just a little reminder. You are looking on the unit circle to find the angle whose cosine is 0. So you're trying to think about where are the x values 0. But you also have to think about what the ranges of these functions are. So if you're looking for arc sine or arc tangent, then the range of these two functions, they want you to look for the answers. This is how they made them be 1 to 1. It's definitely not all the answers that you'll find. Okay, but they're between negative pi over 2 and pi over 2. And when you are looking for arc cosine, the range of that is between 0 and pi. Now, I will say you have your calculator, and you are allowed to use it. You are on paper 3, but just we're trying to think arc cosine. We can only look between 0 and pi. We want to know a place where the x value is 0. So right here on the unit circle. Okay, this is 0, 1. So the cosine of pi over 2, because that's where we are, is 0. So this is the angle whose cosine is 0, and that's just pi over 2. And then we're looking for the angle whose cosine is 1. So we look over here, looking just between here and here. Okay, we're looking for an x value of 1, and that occurs at 0. Okay, so we get pi. And that means that this function is always at a constant pi. which is what we were asked to prove. So you can write that statement again if you want to or not.